Hello students, this is going to be a review of general chemistry that will be useful for the study of climate, atmospheric, and environmental chemistry. So, all matters are made up of atoms, and an atom consists of subatomic particles including protons, neutrons, and electrons. As you can see here, protons are positively charged, whereas neutrons are negatively charged. Neutron, on the other hand, would be neutral in terms of their electric charges. So for an atom to be overall neutral in terms of their electric charges, the number of positively charged protons in an atom has to equal to that of the negatively charged electrons. For instance, for this carbon atoms here, which have 6 protons, there also has to be 6 electrons surrounding them, organized in the form of shells. So most of the mass of an atom actually comes from its protons and neutrons, which together constitute what we call the nucleus of an atom, whereas electrons have negligible mass, but they play very important roles in all kinds of chemical transformation. So we usually represent different elements with their chemical symbol. For instance, H for hydrogen, O for oxygen, so on and so forth. You will be seeing many more chemical symbols later. Sometimes you can see 2 numbers on the left side of a chemical symbol. So what are they? The number Z, right, is what we call the atomic number, which is basically the number of protons in the nucleus, which would be different for different element. And on the top, there would be the mass number, which would be equal to the number of nucleons, which means the total number of protons and neutrons together in the nucleus. So the neutron number is basically just A minus Z, the mass number minus the atomic number. So sometimes you can hear the term isotopes. Well, so what is it? Isotopes of an element have the same number of protons, but they have a different number of neutrons in their nucleus. In other words, they have the same atomic number Z, but different neutron number N and also different mass number A. For instance, for hydrogen, most of the hydrogen atom in the universe is in this form, which is the normal hydrogen isotope, I would say. So this is the most common one, which has atomic number of 1, because it is exactly have 1 proton, but it also have no neutrons, so the mass number would also be 1. There are 2 forms of 2 isotopes of hydrogen. One is the deuterium, which has 1 proton and 1 neutron, making up 2 nucleons in their nucleus. And there is also tritium, which has 1 proton as well, but 2 neutrons, making up a total of 3 nucleons in the nucleus. So to summarize a bit, matter is composed of atoms, each of which consists of protons, neutrons in their nucleus surrounded by moving electrons. So a chemical element actually refers to matter consisting of only a single type of atoms, like C, carbon, H, hydrogen, oxygen, nitrogen, phosphorus, sulfur, so on and so forth. So basically, a chemical element only have one type of atoms in the whole thing. Whereas a lot of the chemicals that you see around you are not a single element. They're usually compounds. So a chemical compound consists of 2 or more atoms of different elements sort of combined together. For instance, H2O, which means this water molecule has 2 hydrogen atoms bonded with 1 oxygen atom in this molecule. CO2 means that there is 1 carbon atom bonded with 2 oxygen atoms in this CO2 molecule. NaCl, sodium chloride, which is basically table salt, is 1 sodium ion bonded with 1 chloride ion, so on and so forth. So I've already mentioned some terms like molecule and ionic compound. So what are they? Ionic compound, basically different atoms losing and gaining electrons to form charged species called ions, right? Which are then bonded together by very strong electrostatic forces. For instance, table salt, NaCl, sodium chloride, is actually formed by sodium losing an electron to chlorine forming sodium ion, which is a positively charged ion because it has lost an electron, and also chloride ion, which has gained an electron and thus it is negatively charged. And these two, one positively charged, one negatively charged, have strong attraction to each other, and they sort of attract each other to form a very strong ionic bond, forming this sodium chloride. There is another very important kinds of compounds called covalent compound. They're basically different atoms bonded together to form overall neutral species called molecules by the sharing of electron pairs. For instance, water, very common compounds around us and very important for life, of course, is basically formed by two hydrogen atom and one oxygen atom bonded together by the sharing of electrons among them. So we'll go deeper into how these bonds are formed in the next few slides. To understand bonding, it is very helpful to first consider the electronic structure of different elements. A very helpful model is to think of electrons as being organized in shells. So the shell closest to the nucleus, the first shell, can only host 2 electrons. So for instance, for hydrogen, which has only one electron, then the first shell is only occupied by 1 electron. And for helium, which has 2 electrons, then the first shell is occupied fully. Then for lithium, which has 3 electrons, the first shell would already be occupied by 2 electrons and is thus full. And then the next shell would be occupied by 1 electron. So the second shell can be occupied by at most 8 electrons. So going from lithium to neon here, you can see progressively you have 1 electron in the outermost shell in lithium, and then beryllium have 2, boron has 3, carbon has 4, so on and so forth until neon, which has 8 electrons in the outermost shell, and it is very happy, right? So these diagrams here are called Lewis diagrams. But they are basically a representation of the electrons in the outermost highest occupied shell, or we call it the valence shell, all right? So bond formation actually involves the electrons in the outermost or valence shell, and a complete outer shell consists of 8 valence electrons, as I've just mentioned, except, of course, hydrogen and helium, which only have 2. And breaking a bond leads to a release of energy. And to form a bond, you require energy. And generally, double or triple bond energies are higher. And in essence, especially in the covalent bond, right, one bond basically means the sharing of 2 electrons. Well, first, going back to ionic bonds. So as we've mentioned, ionic bonds are formed by electrostatic attraction between positive and negative ions, all right, formed by electron transfer. So a very common example is sodium chloride. So here you can see the valence shell structure. So sodium have 2 electrons in the first shell, 8 electrons in the second shell, and then in the valence shell, the third shell, there's 1 electron. So you can think of sodium chloride as being formed by sodium giving up this valence electron to chlorine, all right? And chlorine has 7 electrons in its valence shell, so it is missing 1 in order to be full. So it would happily accept 1 electron from sodium. So after accepting this electron from sodium, sodium would become positively charged, all right? And then chlorine would become negatively charged. So now you have 2 opposite charges attracting each other and thus forming a strong ionic bond. But a lot of molecules are not bound by ionic bond. They form covalent bonds instead, which are basically sharing of paired electrons. For instance, this is a molecule of methane, CH4, which basically is 1 carbon atom sharing electrons with 4 hydrogen atoms. And for each of these bonds, they are basically 1 hydrogen atom sharing its valence electron with 1 valence electron from carbon. And this sharing of paired electron together, each electron contributed by each of the atom, would form a bond, and this bond is called a covalent bond. And you can see CH4 has 4 covalent bonds in total. The carbon is bonded to each of the 4 hydrogen atoms through covalent bond. A special kind of covalent bond is called polar covalent bond, which means 2 atoms from different elements sharing the electron unequally, right? And we'll return to this, and this has to do with the different electronegativity of different atoms, and we'll come back to this later. Let's elaborate on covalent bonds further. As we've mentioned, hydrogen shares electron until it is surrounded by 2 electrons, okay, making its valence shell full. For instance, so you can see hydrogen atom with 1 electron sharing with another hydrogen atom also with 1 electron. So as these 2 hydrogen atoms are bonded with each other, they're essentially sharing electron with one another, forming a bond with 2 electrons. So for each of the hydrogen atom, their valence shells are filled with 2 electrons. So both of them would be happy, and this is why they form this bond. And this is also why most of the gases would form a diatomic molecule. And atoms other than hydrogen share electrons until they're surrounded by 8 valence electrons. We call it the octet rule. For instance, oxygen atom have 6 valence electrons in their outermost shell, so they're missing 2 in their valence shell, so they would like to form 2 bonds. And so for instance, if they share electrons with hydrogen to form H2O, you can see the structure, the Lewis structure would be like this. So on each side, you have 1 hydrogen atom sharing its electron with oxygen. This hydrogen atom also sharing its electron with oxygen. So from the perspective of the oxygen, its valence shells are then filled with 8 electrons. 2 of them are shared by the hydrogen atoms together. And for each of the hydrogen atom, its valence shells are also filled with 2 electrons. Right? So for both oxygen and hydrogen atoms, they are all happy, and that's why they form this molecule, water. The same goes with sulfur. Sulfur also has 6 valence electrons, missing 2 electrons in their valence shell, so they would like to form 2 bonds, such as in the case of H2S, hydrogen sulfide. For fluorine and chlorine, I should say, they have 7 electrons in their valence shell, so they are missing 1. So they would always like to form 1 bond, another atom to share 1 electron with them. So that's why they would like to form HF and HCl, which is hydrochloric acid and hydrofluoric acid with hydrogen. Okay, so now then, after forming these compounds, both of the atoms are happy by having their valence shell filled. More examples. So carbon has 4 valence electrons, so they're missing 4 in their valence shell, so they would like to form 4 bonds to fill up its valence shell up to 8 electrons. So that's how methane is formed. Carbon atoms sharing 4 electrons with 4 hydrogen atoms, right? Each of which would donate or share 1 electron. So forming this methane, CH4 with 4 hydrogen carbon bonds. Nitrogen is a very interesting case. So nitrogen has 5 valence electrons, so missing 3, thus it would like to form 3 bonds. Okay, so in ammonia, NH3, you can see the N is forming 3 bonds with 3 hydrogen atoms respectively. But what is interesting is that you can see there is a pair of electrons, both of which originally from hydrogen, that are kind of just standing alone there. It is not forming any bond, but it is very happy on its own because it has 2 electrons here as a pair already. So we usually call this a lone pair, all right? Oxygen is another interesting case. Oxygen, again, have 6 valence electrons. So when oxygen atom form bonds with itself, they're essentially sharing 2 electrons with each other, forming 2 bonds here. We call it a double bond, okay? And then on each of the hydrogen atom, you can see there are two lone pairs on each side of the oxygen atoms. So this is molecular dioxygen. There are another class of chemicals called radical. What are they? A radical is a species with an unpaired electron. So in all of the examples of compounds that we have seen before, all the electrons are paired in the final chemical structure, right? But radical would have unpaired electrons. For instance, this HOH hydroxyl radical, okay? You can see oxygen has 6 valence electrons to begin with, and hydrogen has 1 valence electron to begin with. So in total, they have 7 valence electrons, all right? But so there is like basically 1 electron that is alone without any pairing with another electron. So we call it a radical species because electrons always like to be paired. So this unpaired electron would render this whole molecule having high energy, okay, to have high energy, and it has high tendency to actually pair the electron to reduce the free energy. So it is highly reactive whenever it has a chance to grab electrons from another molecule or bonds, it would like to do so, all right? So they often are involved in very rapid reactions, and indeed, radicals drive a lot of the atmospheric gas phase chemistry. So you can see there are other examples of radicals, and whenever you see radicals, they're usually very reactive because the lone pair, not lone pair, because the unpaired electrons are not very happy on its own. It will always like to grab electrons from other species and thus oxidizing other species. I just mentioned the term oxidation, and we'll come back to what oxidation actually means very soon. So many of the compounds of environmental interest are organic compounds, which means compounds that have a lot of at least one and more carbon-carbon bond or carbon-hydrogen bond. So here I'm just going to give you the names for the broad classes of common organic molecules, just so you know. So for the first class is what we call alkanes, which contains only carbon-carbon single bonds. For instance, this molecule C2H6, which we call ethane, contain 1 carbon-carbon bond and 6 carbon hydrogen bond. Another class is called alkenes, which contain carbon-carbon double bonds. Okay, so here you can see this carbon molecule atom and this carbon atom are bonded together by a double bond, a sharing of 4 electrons instead of a sharing of 2 electrons. All right, and there are fewer electrons left to share with hydrogen, so there are only 4 hydrogen atoms in this compound. And then a third class is called alkynes, which contains carbon-carbon triple bonds. All right, so this carbon atom and this carbon atom have a triple bond between them, which is basically a sharing of 6 electrons. All right, leaving only 1 more electrons to share with hydrogen on this side and another electron shared with hydrogen on this side. A very important class of compounds is called aromatic compounds, which contain what we call the aromatic ring, which are 6 carbon together, sharing electrons in such kind of arrangement. And by the way, these electrons are actually not localized in local bonds between the carbon atoms, but they're actually delocalized and kind of mobile around the whole benzene plane. So there are also many different kinds of oxygenated hydrocarbons like aldehyde, alcohol, ketones. Alcohol are very common. For instance, methanol, ethanol, basically they contain the hydrogen hydroxyl functional group. Acetic acids would have the CO2, OH, all right? And acetaldehyde, which is a kind of aldehyde, would have the C double bonded with oxygen and also bonded with hydrogen here, all right? So I should clarify what I just mentioned, what functional groups are. So functional groups are atoms or groups of atoms with specific structure and reactivity. All right. So for instance, alkane, basically any carbon-carbon single bond, alkene, carbon-carbon double bond. And when you say the term ether, it has such kind of functional group, carbon bonded with oxygen, which is then bonded with another carbon. We call it ether functional group. Alcohol are anything that has a carbon bonded with oxygen, which is also bonded to a hydrogen, right, in such kind of arrangement. And anything like this would be considered alcohol. Aldehyde, again, is carbon bonded to another carbon that is double bonded with a oxygen and a single hydrogen atom on this side. Ketone are kind of like aldehyde, but instead of having a hydrogen bonded with the double bonded oxygen, carbon oxygen group here, this carbon that is double bonded with oxygen would be bonded with one carbon on this side and another carbon on another side. Carboxylic acid, very important class of organic compounds, very common in soil. They are basically having this kind of functional group, having a carbon atom double bonded with a oxygen, and also an hydroxyl functional group on the other side. All right, so this is carboxylic acid. So one example is, a carboxylic acid with two carbon in total, two carbon atoms in total, and that is acetic acid. Basically what make up a vinegar. So ester is again something that is similar to carboxylic acid, but instead of having an oxygen, a hydrogen there bonded with the oxygen, this oxygen here will be bonded with another chain of organic compounds. So this R basically just means anything that has a carbon in it bonded with many other different things. So we call this ester group. So in addition to many different kinds of organic molecules in the environment, there are a lot of ionic compounds, most of which are inorganic as well. For instance, ammonium, which is basically nitrogen bonded with 4 hydrogen atoms, and together they become an ion with a positive charge. All right. Acetate is actually organic, which is basically acetic acid having lost deprotonated, okay, having lost a proton, all right? And nitrate, nitrite, so on and so forth, and carbonate, sulfate, sulfite, silicate, phosphate, all of these are very important in the environment. They are charged species, they are ions, right? They are very important, especially in water solution, including in aerosols, clouds, oceans, rivers, lakes, so on and so forth. But they are not that important in the gas phase, except very high in the atmosphere where you have the ionosphere. So how do chemists quantify the amount of different chemical compounds or elements? A very important concept is mole. So mole, or the scientific notation MOL, is a chemical unit. 1 mole equals to 6.02214 times 10 to the power of 23 atoms, ions, or molecules. So 1 mole is a whole bunch of stuff. Another concept then is the molar mass, basically the mass of 1 mole of an element or compound. To give you an example, for instance, the molar mass of oxygen gas. What is the molar mass of oxygen gas, which has a chemical formula of O2, 2 oxygen atom bonded together by a double bond, okay? So the molar mass can be calculated by considering the fact that this molecule has 2 oxygen atoms, all right? And each oxygen atom have a mass number of 16. And if you look at the atomic mass of oxygen atom, each oxygen atom would have a standard atomic weight of 16, which means that each mole of oxygen atom would have a mass of 16 grams. So since oxygen gas is a dioxygen molecule with 2 oxygen atoms, so the molar mass of oxygen gas, which means the mass of 1 mole of oxygen gas, would be 16 times 2 gram per mole, which means, of course, 32 gram per mole. All right. So again, this 16 is the standard atomic weight of a normal sample of naturally occurring oxygen atom. So the total mass of any compound, of course, would be the total number of moles, the quantity of this compound or element times the molar mass. After knowing how to quantify different chemicals, now it's time to talk about reaction, the most exciting part of chemistry. So a chemical reaction often would involve, of course, reactants and then products. For instance, we usually represent a chemical reaction like this, right? A bunch of things reacting, forming the products. So here, the big A and B are the reactants. The C and D here are the products. And the small a, b, c, d here are the numbers of molecules or moles of reactants and products that are required to balance the chemical reaction so that the total number of atoms on this side or for a particular element would always have to be the total number of atoms on this side for that given element. For instance, consider this reaction, which is basically the combustion of methane gas in air. All right. So when methane is burned in air, it's basically being oxidized to form carbon dioxide and releasing water vapor along the way. Again, we'll talk more about what oxidation means very soon. So in this particular reaction, methane being oxidized by half of an oxygen molecule. All right. So for this combustion reaction above to be complete, you can see it is basically one molecule of methane reacting with two molecules of oxygen gas to produce one molecule of CO2 and two molecules of H2O. So that you can see here on this side, it has one carbon atom on this side and it has one carbon on this side. So it is balanced. It has 4 hydrogen atoms in total on this side and 2 times 2. Also 4 hydrogen atoms on the side. So this is also balanced. What about oxygen? You have 2 times 2. 4 equals 4 oxygen atoms together on this side. And here you have 2 oxygen atom here and 2 oxygen atom here as well. So also 4. So you can see that this reaction is balanced. So this describes the complete combustion reaction where methane is oxidized to form CO2 and water. I've already mentioned oxidation a couple of times, so what exactly it is? So now we are moving on to a very important topic of oxidation and reduction, which is the opposite of oxidation. So what are they actually? Oxidation, chemically speaking, means a loss of electrons, and reduction is a gain of electrons. So for instance, when we say sodium loses an electron to chlorine to form sodium chloride, sodium is essentially oxidized and chlorine is essentially reduced. All right. A good way to remember this is Leo, the lion, says grrr. All right. Where Leo, you can see loss of electrons means oxidation and gain of electrons means reduction. All right. If it helps you. Another important concept related to this is the oxidation state or oxidation number. Oxidation number of a compound or an atom is a measure of how oxidized it is, also meaning how much electrons it has lost or it is losing. So more positive number means more oxidized and more negative numbers means more reduced. So when a species is oxidized, okay, its oxidation number would increase, whereas if a species is reduced, its oxidation number would decrease, okay? So for a charged species like an ion, like sodium ion or chloride, its oxidation number is simply its charge, all right? So electrically neutral species would have an oxidation number of 0 as a whole. So here, sodium obviously has an oxidation number of +1, and chloride here has an oxidation number of -1. But for an atom within a covalent molecule, its oxidation number actually depends on the relative electronegativity of other atoms that it is bonded to. Okay, so the overall molecule is usually neutral, so the overall molecule would have an oxidation number of 0, but each atom within the covalent molecule may actually have an oxidation number depending on whether that atom has the electrons closer to it, or would some of the atoms or competing atoms would have more electrons toward their side. Okay, so this electronegativity, basically meaning the love of electrons, is a very important sort of consideration of how oxidized an atom is within a covalent molecule. So electronegativity, or the love of electrons, is the tendency to attract electrons. They can actually be kind of inferred from a periodic table, the position of these elements in the periodic table. So here, I'm showing you the periodic table. You can see the highest electronegativity here is usually on the top right side of the periodic table, and the bottom left side would have the lowest electronegativity. It makes sense because the elements here, the atoms here, usually they have their valence shell nearly filled anyway, so it is easier, or they have a higher tendency to they want to attract electrons to fill up their valence shell. Whereas the elements on this side, usually their valence shell is only filled with maybe 1 or 2 electrons. It's very hard for them to fill up the whole valence shell anyway. They would be better off by just like giving up their electrons so that their valence shell, the next valence shell, would be filled. So here, for the major elements found in life, in descending order of electronegativity would be oxygen, which usually have a very high electronegativity, and then nitrogen, and then sulfur, which is roughly the same electronegativity with carbon, and then hydrogen and phosphorus. So, all right. So you can see among these elements, oxygen has the highest electronegativity, and hydrogen would have the lowest. So oftentimes oxygen and hydrogen can just be considered to have an oxidation number of -2, okay, and +1 respectively in various compounds, because usually in an organic molecule or in a compound, oxygen is usually the most electronegative element, and hydrogen is usually the least electronegative element within that molecule. So the oxidation number of all atoms in a neutral molecule has to sum up to 0. So knowing that oxygen has an oxidation number of -2 always, and hydrogen have an oxidation number of +1 always, using these two pieces of information, one can usually figure out the oxidation number of other elements within a molecule. And now I'm going to give you some example. So oxidation state, again, describes the positive or negative character of atoms or the degree of oxidation. For ionic compounds, it's very simple. The oxidation state is just the same as the charge on the ion. For instance, sodium chloride, within sodium chloride, sodium has an oxidation number of +1 because it has a charge of +1. And chloride has an oxidation number of -1 because it has a negative charge of -1. All right? But of course, the sum of oxidation numbers within the whole ionic compound has to be 0, okay? Because the charges, of course, have to balance each other. For covalent molecules, it is more arbitrary. Again, it is really dependent on the electronegativity scale, comparing the electronegativity of different atoms. And usually, we use the rule of oxygen having an oxidation number of -2 always, and hydrogen having an oxidation number of +1 always. For instance, in this example, in methane, CH4, hydrogen has an oxidation number of +1, and 4 of them make it +4. So within this overall neutral molecule, okay, the overall oxidation number has to be 0. So it means that carbon has to have an oxidation number of -4 in order to balance the +4 from the 4 hydrogen atoms. All right. So in this molecule, carbon has an oxidation number of -4, meaning that it is pretty reduced. So what about in CO2? In CO2, you have 2 oxygen atoms, right? So making an oxidation number of -4 here, right? Because each oxygen atom has an oxidation number of -2. So for this to be overall neutral or having an oxidation number of 0, then carbon has to have an oxidation number of +4, which also means that in this molecule, CO2, carbon is pretty oxidized. Which also makes sense. If you remember from a few slides ago, we showed you how the oxidation of methane, literally by oxygen gas, okay, actually turn carbon from a more reduced state to a more oxidized state, all right? And that is also why we call this reaction an oxidation reaction, all right? Carbon is being oxidized in this combustion reaction, literally by oxygen gas. So one thing to note is the atmosphere is generally a highly oxidizing medium because it has a lot of oxygen gas and also a lot of hydroxyl radical from the photolysis reaction happening in the atmosphere. And because the atmosphere is so oxidizing, this is also the reason why usually in the atmosphere or in the environment in general, which has a lot of oxygen around, oxidation generally would gives out energy, and reduction would usually require energy in order to proceed. So here I have already started talking about energy. So next we'll really discuss what energy means in chemistry. We've already started the discussion of energy in association with any chemical changes. Indeed, it is the relative differences in energy of reactants and products that actually determine how likely a chemical reaction is to occur under given conditions. So a very useful quantity to consider is the change of enthalpy. So what is it? Change of enthalpy of a reaction or transition is the energy released or absorbed as heat at constant pressure. At constant pressure is a very important criteria here because most reactions happening in the environment are under constant pressure. So here, delta H, the change of enthalpy, is equal to the change in temperature multiplied by a heat capacity at constant pressure. So delta H itself depends on temperature, but it is independent of the reaction path. So here I'm showing you the reaction path, basically how energy is changing or enthalpy is changing from reactants to products during a chemical reaction. There are two major kinds. So here I'm showing you reactants and products. Usually for a chemical reaction to proceed, some activation energy has to be overcome in order for this reaction to proceed. In this example, as reactants are overcoming activation in energy and finally becoming products, if the products have lower enthalpy than the reactants, then delta H is negative, which practically means that heat is being released during this reaction. We call such kind of reactions exothermic. Whereas if the final products have a higher enthalpy than the reactants, then delta H is positive. Heat is absorbed during this reaction. We call this kind of reactions endothermic. Since for this kind of reaction, energy is required to be absorbed as heat, this is usually less likely already to occur. On the other hand, exothermic reactions are generally more favored in a given environment. But of course, the spontaneity of a chemical reaction also depends on the changes in entropy, not only enthalpy, but that would be left for a more advanced discussion in the future. So for now, it is good to understand or just to have a rule of thumb, exothermic reactions are generally more favored in a given environment. And in a highly oxidizing environment like the Earth's atmosphere, most of the time oxidation reactions are exothermic and they are thus favored, and they usually release energy along the way, whereas reduction reactions usually are endothermic in a highly oxidizing atmosphere, and they generally require the absorption or uptake of energy for this to occur. Some example, of course, is respiration, which is exothermic under oxidizing atmosphere, and photosynthesis, of course, would be endothermic in the highly oxidizing atmosphere. So we've actually just begun the discussion of thermodynamics, which basically asks the question, can a reaction or transition occur? How likely is it to occur under a given environment? And we have to basically consider the relative changes in energy of reactants and products. For instance, we have mentioned how an exothermic reaction is usually favored in a given environment because it releases energy to the environment, thus raising the entropy of the environment. Whereas endothermic reaction would require a supply of energy for it to occur. Another important aspects of chemical reactions is kinetics. Kinetics basically asks the question how fast a reaction or transition can occur. Sometimes a reaction can be exothermic, releasing energy ultimately, but it may not occur at a noticeable rate in the environment because it has some kinetic constraint. For instance, maybe the activation energy is too high. So without some catalyst or some spark, so to speak, to overcome this high activation energy to begin with, even an exothermic reaction cannot occur very readily in a given environment. So kinetics is really about how fast a reaction can occur. So now let's first dive deeper into chemical kinetics. A balanced chemical reaction does not always represent the actual steps of the reaction pathway or mechanisms. Oftentimes, the overall reaction can be broken down into many different steps, and we call these steps elementary reactions. And some of the, usually one or two of the elementary reactions are particularly important. They would be called the rate determining step, which is basically the slowest step which determines the maximum rate of an overall reaction. Very importantly, the rate of an elementary reaction can be expressed like this. For instance, for this reaction, A plus B becoming C and D, A and B being the reactants and C and D being the products, in this forward direction, the rate of reaction, which is also by definition basically the rate of change of the reactants, okay, per mole or per molecule of A, which is, of course is also the same as the rate of change of the concentration of B per mole or molecule of B, and which is also equal to the rate of appearance of C per unit of, or per mole or per molecule of C, so on and so forth. All right, so this is like the definition of the rate itself, okay, per molecule or per mole of the reactants or product. This can indeed be expressed like this. The rate is equal to K times the concentration of A to the power of small a, which is the stoichiometric coefficient, the number of mole or molecule of A that has to be required to balance the reaction, multiplied by the concentration of B, okay, to the power of B. All right, so only the concentration of the reactants would appear here. Okay, and what is K? K is a very important quantity called the rate constant. Okay, it is not always a constant per se. It would be a function of temperature, pressure, and maybe salinity if you're talking about reactions in seawater, so on and so forth. But for a given environmental condition, then K, it would be a constant. Okay, and the rate would be this constant multiplied by the concentration of the reactants adjusted to the stoichiometric coefficient. So for multiple step reactions, we need to actually sum up the individual reaction rates if we are considering the rate of change of a particular reactant or product of interest. Okay, for instance, here let's say there are two reactions going on, A plus B reacting with B becoming C, but at the same time A can also react with D to form B back. And these two different reactions with different rate constant K1 here and K2 here. Then the rate of change of A is not only dependent on the first reaction, but is also dependent on the second reaction. So the rate of change of A should be then negative K1 times concentration of A times concentration of B, because you're considering this reaction here. There has to be a minus sign because it is a reactant. Its concentration should be decreasing over time. But at the same time, this reaction is also going on, so you have to have another term, minus K2 times A, concentration of A, times the concentration of D, basically taking into account of the disappearance of A due to this reaction here. B is interesting because it is being consumed in this reaction but being produced in this reaction. So the rate of change of B should be, first, considering this reaction, minus K1 times concentration of A times concentration of B, accounting for the disappearance of B due to this reaction. But then you also have to consider the appearance of B due to this reaction. So you would have plus K2 multiplied by the concentration of A and the concentration times the concentration of D. All right. So these kind of formulation are very useful when you're considering the rate of change of or how quickly something disappears or something appears, or something is produced when many reactions are involved. So for atmospheric chemical reactions, the concentration of a particular species is usually expressed in terms of the number of molecules per cm cube, all right, and such that the rate of change of this species, basically the rate of reaction, is usually expressed in this term, this unit. The next important aspect is chemical equilibrium. Okay, so thus far we have only considered reactions that is one way, meaning they're irreversible. But indeed, a lot of the reactions happening in the environment are what we call reversible reaction. What does it mean? For instance, A and B can react to form C and D, but at the same time, C and D can also react to form A and B back. Such kind of reactions is called reversible reaction. We usually write it out like this: A plus B becoming C plus D, but there is a double-ended arrow here, signifying that this is a reversible reaction. A and B can become C and D, but C and D can also react to become A and B. They are actually separate reactions, so A and B becoming C and D is one reaction with a rate constant Kf, which means the forward reaction for the rate constant for the forward reaction. C and D reacting to become A and B back, we call it the reverse reaction with rate constant Kr, right? So let's look here at the time progression of the reaction. Let's first assume at the beginning of the reaction, the forward reaction is faster because you have a lot more A and B than C and D, so the forward reaction is faster. But as time goes on, more A and B react to become C and D, so the forward reaction would decrease in rate, would become slower and slower, whereas because you have more and more C and D over time, the reverse reaction would also be faster over time. At some point, if you wait long enough, the forward reaction and the reverse reaction would be equal in rate, okay? And at that point, we would call the system to be at equilibrium, chemical equilibrium, where the forward and reverse rates would become equal, all right? So Kf times A times B would equals to Kr times C and D, and that would characterize the steady state or chemical equilibrium. If you rearrange it a little bit, you can see C times D divided by A and B would be equals to Kf divided by Kr. These are constants, so of course the quotient would also be a constant. At equilibrium, we call this constant the equilibrium constant, all right? Which is not, of course, also a function of temperature, pressure, salinity, and other environmental conditions. But for given environmental conditions, then of course this would be a constant. Okay, so that is a very important concept governing the behaviors of or the concentrations of different reactants and products in the environment of a given condition. But if this ratio more generically is called the reaction quotient, which would only be the equilibrium constant if the system is at equilibrium. But let's say if the system has not arrived at equilibrium yet, then this ratio is simply the reaction quotient. And comparing the reaction quotient with the equilibrium constant can actually tell us where the reaction should be going. Should more forward reaction be occurring, or should more reverse reaction be occurring? All right, would the system be shifting to the right or shifting to the left? If Q is smaller than K, all right, which means that there are more concentrations of A and B than at equilibrium. So the forward reaction would then dominate over the reverse reaction, and the reaction will shift to the right. More in A and B would react to form C and D. But if Q is bigger than K at a particular moment, okay, that means there are more C and D than at equilibrium. The reverse reaction would then dominate over the forward reaction. The reaction will then shift to the left, okay? More, so to speak, the product would turn back to the reactants, until the system becomes at equilibrium again. An important concept to note about chemical equilibrium is the Le Chatelier principle, which states that perturbation of a system at equilibrium would cause the system to shift to minimize the perturbation. So if you do something to a system at equilibrium, then the system would want to respond in a way to minimize that perturbation. For instance, very simply, let's say a system is at equilibrium, okay? If suddenly you add more A to the system, all right? Then the system would like to respond in a way that minimizes the addition of A. What would it do? It would shift the equilibrium to the right, consuming more A, at the same time also consuming more B to form more C and D, all right? So it can also be thought of as, understood as, if you add more A, then suddenly you raise the forward reaction rate. So there will be more forward reaction going on, okay, until the system comes into equilibrium again. Likewise, let's say it's originally at equilibrium, but then you add more of the product. Let's say you add more C, okay? Then you're suddenly raising the rate of the reverse reaction. The system would want to respond to minimize the addition of C. The system would then shift to the left. More C and D would be consumed to form more A and B. You can also use the Le Chatelier principle to understand equilibrium shifts, okay, when we change the temperature of the system. For instance, let's assume that A plus B becoming C and D, the forward reaction is an endothermic reaction. It would absorb heat along the way. Now, beginning with an equilibrium situation, if you suddenly increase the temperature of the system, adding more heat to the system would like to respond in a way to minimize the additional heat. So the reaction would indeed shift to the right, because by shifting to the right, right, then more endothermic reaction, A and B becoming C and D, would happen, and the endothermic reaction would then absorb the additional heat that you supply to the system. Likewise, if the forward reaction is exothermic, all right, A reacting with B becoming C and D would release energy. If you raise the energy, or if you add heat and raise the temperature of the system at equilibrium, then this reaction would shift to the left, because the reverse of this would be endothermic, and thus the system would like to shift to the left in order to absorb the additional heat that you supply to the system. So now we can begin to discuss what kind of reactions are important, what kind of equilibrium reactions are important in the environment. Here in particular, we are considering those reactions that are important for the aqueous phase, meaning reactions happening in solution, in water, right, in natural waters. The first important class of equilibrium reaction or transformation is gas-aqueous phase equilibrium, governed by the Henry's law, which basically is just about gases in the atmosphere dissolving into natural waters to form a solution. For instance, here A, gas species A, all right, G means a gas here, dissolving to form the aqueous solution in water, all right? And at equilibrium, the ratio of the concentration of A in aqueous phase to the partial pressure of A in the gas phase would be a constant, and we call this constant the Henry's law constant, Kh. Another important class of equilibrium reaction is acid-base equilibrium. A lot of the species are what we call acids, which means that they can dissociate to form proton and the conjugate base, right? So H plus the 8 minus from this here. So in acid-base, so proton is basically what give the solution its acidity, all right? And at equilibrium, the ratio, H plus times A minus divided by the concentration of HA, the undissociated form in the solution would also be a constant. We call it the acid dissociation constant, Ka. Another important class is basically dissolution of solid, all right? Solid aqueous phase equilibrium or solubility product equilibrium. So a lot of minerals, for instance, calcium carbonate or sodium chloride, right? But sodium chloride usually dissolve completely. But for a lot of solid which does not dissolve completely, they are usually, when they're put in water, they're usually in equilibrium with the solution, like calcium carbonate, for instance. So XY as a solid, as a mineral, okay, when they're put into water, they can dissolve partly to form the X ion and the Y ion, right? The positively charged ion and the negatively charged ion here. And the solution is also controlled by equilibrium constant, Ksp, solubility product, which is equal to the product of X 2 plus times Y 2 minus, right? Finally, last but not least, water itself in the solution can also dissociate. All right, water as a liquid can also dissociate to form proton and the conjugate base, which is the hydroxide ion. Okay, and this, the product of proton times hydroxide ion, is also a constant. We call it the water dissociation constant, Kw, and it has a very specific value, 10 to the power of negative 14 actually, mole. And another very important concept is pH. pH is by definition the negative of the log 10 of the concentration of proton in mole, right? Mole, the big M, okay, is basically the number of mole per liter of the solution. So there is some negative here. So if you have a higher concentration of proton in the solution, then pH would be lower. The solution would be more acidic. And very importantly, when you look at the water dissociation constant here, you can see that if the solution has more proton, if the solution is more acidic, then correspondingly, there will also be a lower concentration of hydroxide radical, right? The solution would be less alkaline. Now, let's go deeper into acid-base chemistry. Acids are proton donors. They can react or dissociate to give protons to the solution, whereas bases are proton acceptors. Okay, so for instance, BOH here can receive a proton to become B plus and forming water again. Here, some other important terms. When an acid dissociates to form proton, the HA here is called conjugate base, right? Here, when a base accepts a proton, then this thingy is called conjugate acid. Okay, so acids can be strong or weak. Strong acid is an acid that dissociates nearly completely in a solution. For instance, sulfuric acid basically dissociates almost completely to form 2 protons and 1 sulfate in the solution, right? I mean each molecule of sulfuric acid. Nitric acid also almost nearly completely dissolved in solution. Nitric acid forming proton and nitrate, all right? Okay, so we usually don't use the double-ended arrow here because it is not that reversible. Once they dissolve, they are almost like all in the dissociated forms, all right? The dissociated ions form. But there are a lot of acids that are weak acid. Weak acid is an acid that dissociates only partially, and the concentration of itself and its conjugate base is governed by the acid dissociation constant, Ka, as we have already mentioned before, the pH of the solution, which is related, of course, to the concentration of proton, and of course also the total amount of weak acid that we add to the solution. For instance, here give you a very simple example of acetic acid. Okay, acetic acid is the acid that appears in vinegar. So if we dissolve a certain amount of acetic acid into the solution, then it would dissolve first. After dissolving, it can dissociate to form proton and the corresponding conjugate base, which is the acetate, okay, acetate ion. And we know that this is governed by the concentration of all of these things are governed by the equilibrium constant, dissociation constant, which is a proton times acetate concentration divided by the concentration of dissolved aqueous phase acetic acid. Okay. And so we have one mathematical relationship relating all of them. We also have the water dissociation constant to relate the concentration of proton with hydroxide ion. And we also have this very important reaction, which is basically mass balance equation, because we know how much, we begin by knowing how much acetic acid we add to the solution. So we know how much in total we have added. And this total has to be equal to the equilibrium concentration of the dissolved undissociated aqueous phase acetic acid and the dissociated acetate ion. This is basically just mass balance equation. So how can we quantify the concentrations of different ions and species in the system at equilibrium? We're first giving you an example here. So let's say we dissolve 0.01 molar of acetic acid in pure water. All right. Again, molar means the number of mole per liter of solution. 0.1 molar of acetic acid in pure water. What is then the equilibrium pH of the solution? Okay. So now, first let's look at this. This dissociating to form proton and acetate, and you have this equation here which relate these three concentrations together by the acid dissociation constant. You also have this here. We know this has to be 0.01 because this is the total amount that we have added. Part of it would be dissociated to form acetate, and some of it would remain in the form of acetic acid, all right, undissociated, and the sum of them, of course, has to be equal to 0.01. Now we have two equations, right? One equation here and another equation here, okay? But we have three unknowns, right? We don't know this, we don't know this, we don't know this, which is, of course, equivalent to pH, okay? All right, because we know pH is negative log 10 of this. So we have three unknowns. We don't know pH, we don't know this, we don't know this. So we need one more equation, okay? If we have three unknowns, we need at least three equations. We need exactly three independent equations in order for us to know all three quantities unambiguously. So we bring in one more equation. A very useful one is what we call charge balance. Basically, sum of charges of all ions has to be zero. Okay, has to be zero. All right. So this is a very important. We know it has to be true because the overall solution is not charged. So the sum of all of the positive ions and must be equal to the sum of all of the negative ions. Okay. So here in this solution, we only have these three kinds of ions. Okay. We have proton, we have the acetate, and we also have the hydroxide ions because the dissociation of water can form hydroxide ion. All right. So these are the only three charged ions in the system, and the sum of the positively charged and the sum of the negatively charged has to be the same by charge balance. Okay. So now we have a third equation. So if you just work it out, all right, so do substitution and things, you would be able to figure out the concentration of all of them. Here, as an illustration, I would make a further assumption to make the calculation just slightly easier, all right? Here, because we know that this is an acid, so after dissolving into the solution should be acidic. So supposedly there should be a lot more proton than hydroxide ions. So here we make an assumption that this is so small that this can be ignored compared to this. Okay, so H plus would be, or the proton concentration would be roughly equal to the concentration of the acetate. Okay, if you substitute this into this here and then just work out all of them, all right, so here it is 0.01, and then you substitute this to SH, so on and so forth, all right, you can then see that you can then find this equation, okay, and then finding this equation, and of course this is just a quadratic equation of proton concentration, so you can solve it. After solving it, okay, by the way, Ka, of course we know that as well. Here I'm giving you pKa, which is the negative log 10 of Ka, which is 4.76 for acetic acid, okay. Given this, we can find that, and solving this, we can find that proton is roughly equals to something, and corresponding pH would actually be 3.4. So this is how we can solve for the system, right? Meaning finding the concentrations of all of the species in the system. You have to list all of the unknowns that you have. You have to then align all of the independent equations. So here you have the equilibrium equation, you have the mass balance equation, and finally we bring in another equation, which is the charge balance. We have 3 equations solving for 3 unknowns, and ultimately making some simplification. You can then figure out the concentration of everything, and thus also the pH, which is basically just negative log 10 of the concentration of proton. Later, when you learn about real water chemistry, like the chemistry that happens in the ocean or natural waters like in the rivers or lakes, charge balance may be useful, but we will also introduce some other important concepts such as alkalinity or dissolved inorganic carbon in order to help you solve for the system. But that would be left to the future. Finally, let's talk a little bit more about phase transformation. Phase transformation occurs when a substance undergoes transition to a different physical state without any change in its fundamental chemical composition. So it's not necessarily a kind of chemical reaction. The chemical composition or the chemical nature of that thing hasn't exactly changed. For instance, when liquid water, right, evaporate to become water vapor, this process is called vaporization, and that is a form of phase transformation. And when water vapor condenses to form liquid water, maybe as clouds or rainwater, okay, in the atmosphere, that process called condensation, of course, is also a form of phase transformation. Liquid water freezing to form ice, okay, or ice melting to form liquid water is also forms of phase transformation, of course. And for some solid, like solid CO2, like carbon dioxide, all right, dry ice basically, can indeed vaporize into its gas phase without passing through the liquid phase. And that's indeed why we call dry ice dry, because the vaporization of solid CO2 actually does not involve any liquid phase, all right? And that's why we call it dry ice, okay? And this process of solid becoming gas is called sublimation, and the opposite of that is called deposition. We usually talk about the 3 states of matter, but indeed there is a 4th state of matter. We call it plasma. Plasma is interesting. It's kind of like gas, but it has very special properties that are very different from gas because of the ionization of the gas molecules. So when gas molecules become ionized, maybe because of high temperature or because of the existence of ionizing radiation, such as in the ionosphere, in the atmosphere, okay, they can become plasma, which would have very different properties than the gas. In relation to the aqueous phase equilibrium that we just talked about, phase transformation actually also include the dissolution of a gas or a solid ionic compound into a solvent, such as water, to form a solution. So dissolution itself is also a form of phase transformation. We've already given you some example. If a gas A, okay, dissolve into water to form a solution, this gas aqueous phase dissolution process is also a form of phase transformation. Or when a chunk of ionic solid, maybe calcium carbonate, all right, dissolve in water, or we put it into water, it may dissolve incompletely to form some X2 plus ion and Y2 minus ion, okay, and then the product of them are also tied to the solubility product constant. So now that concludes my very brief introduction or overview of general chemistry that will be useful for the study of climate, atmospheric, and environmental chemistry.